We have been talking about solution of Schrodinger equation in a number of potentials, in a variety of potentials, and so far we have seen three kinds. One is that in which you have a free particle in an infinite potential well. We have seen mostly in one dimension so far, and we have been will be only seeing potential problems in one dimension. Most of it, excepting when we want to talk about degeneracies. And then we have talked about a potential step, and this potential step was solved, and it was solved for energy greater than 0, energy less than, energy greater than the barrier height, which is V0, and energy less than the barrier height, and so on and so forth. Today, mostly we will talk about the bound states and how we actually calculate bound states in a potential problem. All right. So, the bound state, we can study it. Why are bound states important? The bound states are important because the electrons and protons and all these microscopic particles, they are bound to the atom. Okay, protons and neutrons are of course inside the nucleus, but the electron, unless you provide a sufficient amount of energy, it remains bound to the atom. And bound state energies are really the negative energies, so that they remain bound and do not escape. Okay, and we have seen that you might have seen it in the hydrogen atom, that the energy levels of the electron is given by minus 13.6 by n square electron volt. This is the electronic energy levels in various energy states, quantum states, for a hydrogen atom, electron in a hydrogen atom, and this n tells you that which state it is in. So, in the ground state, which is the lowest energy state, it has an energy which is minus 13.6 electron volt with n equal to 1, and this is a negative energy, and this corresponds to a bound state, and that is why we want to understand bound states and finding bound states in a quantum mechanical problem by solving Schrodinger equation. Okay. So, let us take a very simple potential. The potential is of this kind. It is called as a potential well, as opposed to an infinite potential well where the particle was free. Here we are talking about a potential well which extends, say, from minus A to plus A. You can call it L also, does not matter. And this is V naught, and this is your V equal to 0, which means that this is an attractive potential for the particle. Okay, and so this is at x equal to minus A plus A, and you have three regions that are under consideration. There is an energy region 1, there is a region 2, and there is a region 3. Okay, so what you can say is that the potential is equal to 0 for x less than minus A. It's equal to minus V0 for minus A less than equal to x less than equal to A, and again it's equal to 0 for x greater than A. So that's the potential profile, and we have just drawn it schematically. It's a constant potential, it doesn't vary. So this V naught is constant so there's a sudden discontinuity at this x equal to minus A and x equal to plus A, and the particle, we are not saying the particle is inside, we are just talking about the energy of the particle. And we'll be particularly talking about two energies where the energy is greater than 0. Okay, so this is case 1. Energy is greater than 0. Okay, which does not correspond to bound state, corresponds to the extended states, and case 2 where the energy will lie between minus V0 and this. So which means that 0 greater than E greater than minus V naught, and E is negative. So here E is negative, but it is between 0 and the V naught. Okay, so it's somewhere here. Okay, somewhere here is what we are talking about in case 2. So we'll see case 1 and case 2 separately, and we will write down the wave functions in all these 3 regions, and I'll simply write down the solutions. But before that, let me tell you so we are solving this equation, T2 psi dx2 plus V psi equal to E psi. That's a time independent Schrodinger equation. We have both the cases, E greater than 0 and E less than 0, and we have 3 distinct regions, which one of them is left of minus a, the other is between minus a and plus a, and the one that's on the right is x greater than a, and we are going to solve this equation for these 3 regions. Okay, and you can do the simplification if E is greater than 0 and if V is not there, that's for the region 1. We'll simply write this as psi 1 E psi 1, and E is greater than 0. So this is like d2 psi 1 dx2 equal to minus k1 square psi 1, where k1 is equal to root over 2me by h cross square, and for the other one you'll have a minus v naught psi, and then you can again write this thing. So you'll write that you'll have a d2 psi 2 dx2. I will not write this every time, this equation. I'll simply write down the solution, but you should get used to it by writing down the equation. So this is minus k2 square psi 2, where k2 is equal to root over 2m e plus v0. I have to write it a little small, but so this is e plus v0 there inside the the square root, and these are the 2 equations that you have to solve, and both the solutions are known. We'll write it as and of course the region 3, we'll also have to write region 3. Let me write it here. So d2 psi 3 dx2, which is very similar to, so it's a minus k1 square psi 3. The only difference would be, so this is region 1, write it as 1, this is 2, and this is 3. Okay. The only difference would be that between 1 and 3, 1 you'll have this thing, reflected, an incident and a reflected wave both, and so that's the wave which goes in the left as well as in the right. This one will of course have a sine and a cosine solution, because you are considering a short span of space here. This one, even though it formally exactly looks like equation number 1, but you'll not be allowed to write down a reflected wave. There'll only be a wave that's moving towards your right. Okay, so we'll write down the solutions, which is what we'll do for So this is equal to exponential I k1 x plus, now I make a simplification. I don't write a and b, I write e exponential I k1 x r exponential I k1 x. Now this means that r is the ratio of the two coefficients such that the mod square of that would give you a reflection or reflectivity or the reflection coefficient. Okay, so this is that amplitude whose, as I said, mod square will give you the, in principle it's complex, the mod square of this will give you the reflection coefficient. Similarly, psi 2, which is there is not much to do here, you simply can write it as a sine k2x plus a b cosine k2x and this is from for this region 2, which is between minus to minus a to plus a, and the third region will simply have a t exponential I k1 x. Okay, so these are the three solutions for these three regions, and so there will be an incoming flux on the first region, and there will be a reflected flux as well. This is a sinusoidal solution and a cosine solution between plus a and minus a. Look, we are not dropping any of this here because there is no infinite potential that exists at minus a, which was the case for the particle in an infinite potential well. So we can keep both the solutions because the wave function does not have to vanish, the psi 2 does not have to vanish at x equal to minus a. So we are allowed to keep both the solutions, and similarly in the third region there will only be a transmitted solution and will not have any reflected component because there is nothing to reflect back on the right side of the potential well. Okay, so that's your so these are your solutions, and so there'll be an incoming flux or an incident flux. Let me write it as incident flux from the left. So this is equal to h cross k1, that's the velocity by, so h cross k1 by m is the velocity, and there is a r mod square. So that's the sorry, this is the reflected one. So this is the incoming flux. The reflected flux is, it's equal to, so this is h cross k1 by m into r square. This is what I've been telling, and there's a so flux inside the well. So this is equal to h cross k2 by m, and you have a mod square minus a b mod square. So this is inside, and the transmitted flux is simple because that's the one on the so this is equal to h cross k1 by m and a t mod square. Okay, so these are the incident flux, reflected flux in region 1. Inside the well, there's it's equal to this, and the transmitted flux is given by this. So what is so this the flux should be conserved. So there will be h cross k1 over m 1 minus r mod square, this is equal to um, h cross k2 over m and a mod square minus b mod square. It's equal to it's h cross k1 by m and a t mod square. Okay, so that's the continuity of the flux. Now what you have to do is that you still have to calculate r t, even though we have reduced the number of coefficients by using this ratio r and t, but you still have r and t, a and b to calculate, and you have 4 unknowns here, and there are 4 equations. The 4 equations would be the boundary conditions at x equal to minus a and at x equal to a for both the wave function and the derivative of the wave functions. Okay, so that's what we have to do. So we'll do it here. We come back to this part of the board, and let me uh, erase this. Okay, so we'll match the boundary condition at x equal to minus a. So the equations are to be matched are the continuity of psi, that's the wave function, and d psi dx at x equal to minus a. So that will be exponential minus I k1 a plus r exponential I k1 a. So uh, that's the contribution from the left, and that has to be matched with the contribution from the inside the well, which is region 2, which is equal to a exponential minus I k2a plus b exponential I k2a. That's your matching the psi at x equal to minus a. Now I'll match d psi dx, which gives I k1 exponential minus I k1 a minus r exponential I k1 a. This is quite simple. I k2 a exponential minus I k2 a minus b exponential I k2 a. So we have matched the boundary conditions, both the boundary conditions, that is the continuity of psi and the continuity of d psi dx, and now we'll do it at x equal to plus a. And once when we do that, it gives again the boundary conditions will have to be matched between region 2 and region 3 at x equal to a, and this gives a exponential I k2a plus b exponential minus I k2a equal to t exponential I k1a, and I k2, that's the second one, a exponential I k2a minus b exponential minus I k2a. That's matching the d psi dx boundary condition, and this is equal to I k1 t exponential I k2a. Okay, so we have applied the boundary conditions at both the boundaries. What you want is mostly this r and t, which means that you have to eliminate a and b from these 4 equations, and which is reasonably simple to do, and you can do that easily. I'll simply write down the final result. Uh, Alright, so if you eliminate a and b, you get r equal to I exponential minus 2 I k 1a and then you have a k1 k2 square minus a k1 square. You should check all of these things. Sine 2k2a. I've given you the definitions of k1 and k2, and this is equal to 2k1 k2 cosine ka minus I k1 square plus k2 square sine 2k2a. Okay, and similarly the t will be exponential minus 2i k1a, and then there is a 2k1 k2 and so there is a k2a here, and then there is a 2k2a. This is 2k2a. I'll write a little small, but okay. And the same thing here, the same denominator to go with. Okay. Now you see there is something interesting here. If R, if your V naught is much greater than rather much less than, so if your energy is much greater than V naught, which is what can be that the energy of the particle is far larger than your V naught, basically the absolute value of V naught. Here we are talking about E greater than 0, so it's a magnitude of V naught. In that case your K1 and K2 are almost equal. Okay, and if K1 and K2 are almost equal, then your R goes to 0. Your R becomes negligibly small, which means the reflection goes to 0. But you see, there is something more important than that. There is a sine 2k2 a that can also go to 0 even if this condition is not there. Which means even if E is not much greater than V naught, you can still have sine 2k2a equal to 0, which tells you there will be no reflection there, and in that case your 2k2a becomes equal to n pi, and so what it means is that the 2 into so k2 is the wave vector, let's write it as lambda. This is equal to n pi, and so if the wavelength of the wave is like 4a over n, where a is uh, the width of the barrier, or rather 2a is the width of the barrier. So if the wavelength of the wave is such that it matches this condition where n is the the integer which is 1, 2, 3, etc., then also the reflection will go to 0. So what happens there is that there is a destructive interference in region 1 between the incoming wave and the reflected wave, and that is why the reflection goes to 0, or I mean, so there's a destructive interference between the waves from x equal to minus a and at x equal to a. Okay, and in that case there is a the reflectance goes to 0, in addition to the condition that we have talked about, that is the energy of the particle to be much larger than the height of the, or the magnitude of the height of the barrier. Okay. This is somewhat interesting, but not that interesting, which we are going to see for the case 2 when E is less than 0 but greater than minus V0. So let us do that, and this will give rise to the bound states. So we will take now state the the case 2 when E is So case 2. So which means that the case is E to be greater than V naught, well, minus V naught. Yeah, I mean, in the sense that your energy is negative, but it's greater than minus V naught. So let me just to avoid confusion, I simply say that it is E is less than 0, but you know that it's not below this minus V naught. Okay. Then we'll have these equations that we can write as d2 psi dx square. This is plus a k1 square psi 1, say for example. This is equal to 0, where your k1 is equal to 2m by h cross square v naught plus e. So this square of this, so I can write this as k1 to be equal to root over 2m by h cross square v naught minus mod e. Okay. So this is really taking into account the fact that your energy is minus mod of E, where mod of E is always positive. So this is the situation for mod x greater than A, which means that we are really talking about the region 1 and so mod x is greater than A, which means mod x is less than A, sorry, mod x is less than A, which means that we are talking about the region 2. Okay, so it's between minus A and plus A. So you can write that as 2, for example. And you can also write for region 1 and 3 to be this is, let me write it as 1, and this is equal to plus a k2 square psi 1 to be equal to 0, where k2 is equal to minus 2m e by h cross square. This is equal to 2m mod e by h cross square. Okay, so that's your thing. That's your equation for mod x to be greater than A, which means the regions 1 and 3 are included here. So just to repeat, your region 2 is your mod x greater than less than A, and the other one is that mod x is greater than here mod x is greater than A. Okay, so we will apply the boundary conditions, but before we apply the boundary conditions, this is a very specific case that we take it, and mostly in the context of studying the bound states, we take such simplification, especially when there is a reflection symmetry. So there is a reflection symmetry here, and we will use that reflection symmetry by talking about even states and odd states. We are not talking about even n, we are not talking about n much here, that is the quantum number that goes in quantizing the k. Rather, we are talking about the wave function being even. So as you change x to minus x, if it retains its form, then you call it an even function, and if it changes the sign as you change x to minus x, then it's called as an odd function. So for a region for 0 less than x less than A, we can write this as and the bound states will occur inside the well. Bound states will not occur outside the well. So we are taking inside the well. So we are really taking the right thing. So this is that region 0, 0 less than x less than a. So this is equal to psi of x is equal to a cos k1 x for 0 less than x less than a. And what happens when the other thing, that is x greater than a, that of course is so this is equal to c exponential minus k2x, this is for x greater than a. Okay, so this I'm only taking it the right side of 0. Okay, so that's the right side of 0, because we are now distinguishing between the even functions and the odd functions. And as you know that cosine doesn't change sign as you change x to minus x, whereas sine changes sign. That's why we have not kept the sine here and we have kept the the cosine here. And this of course you'll have a c minus exponential minus k2x for x greater than a. This is the only admissible solution, because if you take a plus k2x, then that will go to infinity as x goes to infinity, and that will hamper the normalization of the wave function. So normalization means what I said is the mod psi square integrated over all space should give you equal to 1. Okay, so that is not there. So this is your even solutions, and we'll talk about odd solutions now. So odd solutions and for the same the right side of this thing. So let me write that even here. And then you have psi of x equal to b sine k1 x for 0 less than x less than a, and this is equal to c again exponential k2x. This doesn't make a difference because you can't keep a plus there. And so these are the even solution and the odd solution. And you see, even and odd only come inside the well, because the well is symmetrically placed about 0. Okay, so on the right side of the well, that's for x greater than a, there is no change in the wave function. Now we'll have to apply the boundary conditions. What are the boundary conditions? The boundary conditions are psi would be continuous across x equal to a here, because we are just considering the right half of the well, and beyond that, and the d psi dx will be continuous at x equal to a. You can do that by applying the boundary conditions on both these things, that is the even solution and the odd solution. But there is a smarter way of doing it which reduces some of your calculations, and that smarter way is saying that instead of both psi and d psi dx being continuous at x, you can say that 1 by psi d psi dx is continuous at x equal to a. Okay, so so that is the so this takes care of both the boundary conditions, as if we have divided one by the other. There is a d psi dx and we have divided it by that. And if you do this, okay, for the even part, so what you do is that you calculate d psi dx and match it at x equal to a. So this will be like, so what is d psi dx for this? It will be a k1 minus sine k1 x at x equal to a. So we'll write it as this. Cosine is minus sine, and then the k1 coming out, and then we'll write it at x equal to a, and that has to be matched with and then you divide it by this a cosine k1a, because that's 1 over psi here. So this will cancel and there will be a tan k1a, and this has to be matched with this one, which is a minus k2c exponential minus k2a divided by c exponential minus k2a. So this c will cancel and this thing will cancel and so on. So you get a k and the minus sign will cancel from both sides, and what you get is that k1 tan k1a is equal to k2, that's coming from here. So this will give me the even states. I'll now write even bound states. The solution of this, we'll see how, and you do the same thing for the odd function, and you get as k1 cotangent, okay, cot k1a equal to minus k2. That's for the odd bound states. So we get two equations. We don't know how to solve these two equations because the solution is not so easy, because you remember that k1 and k2 are coming out, both contain energy. One contain the k2 contains both E and V0. You see the definitions that we had written earlier, and k1 contains only energy. So what you want to solve is there on both the sides, and such equations are, and you cannot take it out and solve it, because it will not lead you to a solution in the, or rather will lead you to an equation which can be trivially solved. But then you know, these are these are things that need to be done. So there are these two equations that we get, and let us now discuss how do we solve them. So now let me also remove the figure, because now you know what figure we are talking about and what what situation we are in. We have already considered E greater than V0, E greater than 0, and now we are talking about E less than 0. Okay. Okay, so so we have two conditions that we have written it there. We have a k tan k1a will give us even states, bound states, and b I mean k1 cot k1a will give you a minus k2 and so on. So let us first deal with the even solutions, and very similarly we can deal with the odd solutions. And so what's that even solution? So k2 is equal to tan k1a. Okay. So let us call k1a to be equal to y, some variable. Okay. In that case, your k2a square or rather k2 square a square, recall the definition of k2 that we have given, which is 2m by h cross square v naught minus e into a square. That's your k2 square. This is your k2 square, and then I write a square. And if you do this, so if you separate it out, then it becomes 2m v naught a square by h cross square minus 2m e a square h cross square, and just call it as lambda square minus, this is nothing but your k1 a square, k1 square a square. That's the definition of this. So k1 square a square is nothing but y square. This is what you have assumed. So this is equal to lambda square minus y square. So what have you achieved so far? So if you put back everything into the first equation, the original equation, that is this equation, then what you get is the following, that you get root over root over lambda square minus y square divided by y equal to tan y. Okay. So what you have done is that you have multiplied by a and divided by a the left hand side and so on, and then you can so I missed a k1 there. Yeah, sorry, there was a k1 here which I missed. So there was a k1, so I multiply both sides by a, so it's a k2a and a k1a here. So the that I take it down, so your y is equal to k1a, and k2a as we have just calculated, which is equal to square root of lambda square minus y square. So this is the equation that you have to solve. Now this equation that you already see that there's a you want to solve for y, because y includes E energy, the mod of E, which is what you want to solve, which are called as the Eigen Solutions of the problem or the Eigen Values of the problem. But then you see that it's there on both sides. You can solve it numerically, that is you can find for what value of y both the sides are satisfied for a given value of lambda. Lambda would be an input to the problem. Okay, and you can solve that, but that solution is not so easy, or I cannot do it standing out here, that you do it numerically. Either you have to write a code or you have to use some MATLAB and Python and things like that. But there is a solution that you can come up with, and the solution is called as a graphical solution. So let's see what that graphical solution gives. Let me come to this part of the board. So, what I'll do is I'll solve or rather plot each one of them, the left hand side and the right hand side, both as a function of y. So let's see how we do that. So this is your y axis, okay, and this is both LHS and RHS. Separately we'll plot them, and what do we see there? We want to see the intersection point of these two plots, that is left hand side and right hand side. Where do they cut each other? So you'll have the tan to be plotted, because tan y is the right hand side, so this is equal to tan so this is RHS, so that is tan y. Each one of them is some tan y for different values of remember y is k1a. So it's different values of energy. We have plotted this tan y, so this is larger and larger values of energy in the negative side, so it's a mod E. And this is another tan y for a different energy, and this is another tan y for a different energy, and so on and so forth. What is it for the sorry, we are plotting the y tan y. can we just come to the one second for this part of the board? So we have converting it into this equation. Okay, this equation which is root over lambda square minus y square and a y tan y, and that's why you know so you plot not tan y but you plot a y tan y here. So these are all y tan y's, and the left hand side which is lambda square root over of lambda square minus y square for some value of v naught, and those values of this thing your energy, you plot them and they look like this. And so on. Okay, so this is what root over lambda square minus y square. So this is the smallest one, say lambda equal to 1. Okay, I mean I'm just saying, so it's 1, and this one is root over 4 square minus y square, and this one is root over 9 minus y. I mean 4 square, I mean it's 2 square, so 2 square is 4 and 3 square is 9, so 9 minus y square. Now, so the solution is given by, let me show it by a color, if you can see that colored here. This is a solution to the problem where the two plots have intersected. There are two solutions corresponding to this value of lambda. So there are two solutions. There's three solutions here. Okay, so now remember, what is this? These are the bound states that are possible bound states for as you increase the energy below, okay, and try to go deeper and deeper into the well, there will be bound states forming the electrons, the particles. Let's not talk about electrons only, that could be electrons also. The particles will get stuck to the wall and will not be able to come out, will have their energies negative, and the solution of that is given by these points. So for a given value of V naught and a given value of E, you have one bound state, and two bound states for a larger value of V naught, and so on and so forth. Keeping the E to be constant, you are simply I mean, which is equivalent. Either you keep your E constant and increase your V naught depth, or you keep your V naught constant and increase E. In either case, you'll have more and more bound states forming. Okay. So if you want to write down the observations here, one observation is that between 0 lambda pi by 2, that's the first one, that's this one here, you have one bound state, one bound state. Okay. And let me, while we are on the job, let me also draw the other one, that is the odd situation, which gives me the solution which is equal to, so whose solution is this. So this for the even, and the odd one will have a solution which is lambda square minus y square equal to minus y cot y. Okay, just like root over lambda square minus y square equal to y tan y for the even bound states. So these are for the odd bound states, and if I plot them with a different color, let's hope that you are able to recognize this color. So this is that. Okay, and this is that color, and so on and so forth. Okay, that okay, let me draw it by a continuous thing, because I have a color, so it's here and it's here, and so on and so forth. You see, for for the first energy, that is this one, there is no odd bound state, okay, because this green line doesn't cut the circle. So there is no odd bound state, but there is an even bound state. So no matter what your energy or the depth of the well is, keeping the energy to be constant, say, no matter what the depth of the well is, you'll always have one even bound state. Even means that bound state, if you take x equal to minus x, it will remain the same, but that's the wave function, form of the wave function, and it's a bound state because the energy is negative, okay. And this is equal to your y cot y, minus y cot y. Okay. I hope you are able to recognize these colors from a distance. And so now you have, if you have 0 less than lambda less than pi by 2, you have one even bound state. Now for the second case, when you have pi by 2 less than lambda less than say pi, you have one even. You see now it has crossed here, okay, and here as well for the this circle. So it has crossed at that blue point and at this point. So there is one even plus one odd bound state. And similarly, you have between pi to 3 pi by 2, you have two even and one odd. And then you have 3, and so the total number of bound states here is 1 in the first case. The second case it's 2, 1 plus 1. The third case it's 3, 2 plus 1, and so on and so forth. So let me give you a simple numerical example which will make things easier. So the question, numerical question, the question is that a proton of mass, let's write it as MP, equal to 1.67 into 10 to the power minus 27 kgs, which is inside a one-dimensional potential well of width V naught equal to well, it's in given in some MEVs, but if you convert it into joules, it's minus 10 to the power minus 12 joules. It is should be given in MEV, but when you convert it, because you have to do it in SI units, so it converted into joules, and it is inside a potential well which has a means the extent of the half the extent of the well. It is 3.65 into 10 to the power minus 15 meters. So that's looks like the in femtometers and so on. If that is the these are given for a proton which is subjected to an attractive potential of this 4 into 10 to the power minus 12 joule, which is nothing but equal to 6.25 MeV. Okay. Now what you should look at, the question is how many bound states are there? Okay. So that's the question, and what you need to do is that you need to find out lambda, which is equal to 2m V naught a square by h cross square whole to the power half, and you have everything now. You know what's m, V naught is given, m is also given, so we'll call it as mp, which is mass of a proton. A is given, and if you put in all these things, you get this as 2. Okay, so that's the I mean uh, that's your value of lambda. Okay, so this value of lambda of course falls between pi by 2 less than lambda less than pi. Okay, we've just discussed that in that case we have two bound states, one even bound states, which means that if we change that to x to minus x, it doesn't change sign, and there is also one odd bound states. The wave function of that bound state is odd, which means if you change the sign of x, it will change its sign. So there are two bound states in the problem, one even and one odd. And if you want to find out what the bound state energies are, which is what is important, so that can be found out if you simply write down this y tan y. This is for the even bound state, which is equal to root over 2 square minus y square, where 2 is because lambda is 2, we have just found out. So this is equal to, so if you do a simplification of this, you get y square y square 1 plus tan square y, this is equal to 4, and if you remember 1 plus tan square is equal to sec square, so this is equal to y square sec square y, this is equal to 4, so which means that y sec y equal to plus minus 2. Okay. Now if you, there is no way but to solve this again graphically, okay, because you just plot y sec y on the left hand side and see where it cuts either plus 2 or minus 2. That will give you a solution. Plus 2 or minus 2 is simply a flat line at plus and minus 2. So if you do that, let's come here. So if you solve this, your y comes out to be 1.02987 and just to remind you that your y is equal to k1a and your k1 is equal to root over 2m e by h cross square, and now you can get your E here, and your E comes out to be equal to the mod E, rather it's equal to 6.63 MeV, or you can find it in joules. Okay, and now you have one even bound state and one odd bound state, so you need to find both. There is an even bound state, and for the odd one you should do it as using that root over lambda square minus y square is equal to minus y cot y. Your lambda is equal to 2 here. Put this and again solve. Your y will come out to be 1.89549, and this gives you a E to be equal to, or mod of E to be equal to 22.45 MeV, which means there is one even bound state occurring at 6.63 MeV, and there is an odd bound state occurring at 22 at energy equal to 22.45 MeV, and so on. So, as lambda square increases, which means the depth of the potential well goes down, that is it increases in the negative x direction, the number of bound states keep increasing, and I drew this this part of this thing like this, and that's where all your tans will, or the cots will intersect. So for very large V naught, you'll have this, all these things will fall in some kind of a straight line, because this the circumference of the circle looks pretty flat and almost like a straight line. And then you'll have the even solutions are spaced even bound states. I'll write BS. Even bound states will be placed at equally spaced at n plus half pi. So these are the even bound states. So they are placed fairly uniformly close to that. I mean, it's not exactly that, but it sort of comes out. And the odd bound states are, one less, or rather it has to be, less, and this is equal to, so this is like n pi over 2. So they are, the odd bound states are placed at n pi over 2, which is of course one less, because you saw that at very low depth there will be no formation of odd bound states, but even bound states will continue to be there. Okay. So these odd solutions are spaced at these are spaced n, not n pi by 2, it's n pi. Okay, it's not n pi by 2, it's n pi. So that's the spacing between the odd solutions, and the spacing between the even solutions is this. Okay. So what we have looked at is, we have tried to find out that as the energy becomes negative, whether they are bound states forming and what are their bound state energies. So we wrote down the Schrodinger equation, wrote down the solution of that. Once we write down the solution, we apply the boundary conditions, we get an equation and the equation does not have a very simple solution. As the free particle inside an infinite potential, well, there was a very simple solution. Your E came out to be n square pi square h cross square by 2m a square or L square, depending on whether you talk about the length to be L or A. And now that was much easier because the energy came out directly. Here the energy is hidden inside an equation. This kind of an equation, this y tan y equal to that root over lambda square minus y square, this is called as a transcendental equation. Okay, and these equations involve the quantity to be calculated on both the sides and in an inextricable manner. So you cannot separate this and find it easily. And then all these y's and lambdas both have lambda, of course it depends on V naught, and y depends upon your energy E. So that if you have to have that, then a graphical solution is the best, and this is what graphical solution is obtained, where we individually plot both the sides and see for those intersection points, because at the intersection points both the sides have exactly same value, which means those are the values for which the equation is satisfied. Okay, and this is how we calculate the bound states, and this mostly these bound state discussion is put into whether there are even bound states, that is the nature of the Eigen solutions of the bound states, whether they're even bound states or odd bound states. So we have found that there are even bound states, okay, and there are odd bound states, and and their individual, their energies for a given problem. Okay.